picture the fastest thing you've ever seen, a bolt of lightning, a fighter jet breaking the sound barrier. Now forget it, because light is 40 million times faster than sound. Even light takes 4 years and 2 months to reach Proxima Centauri. We sadly don't travel at the speed of light, so how long would it actually take us? If you're the kind of person who wants to feel that sense of cosmic awe, please subscribe to the channel. Now let's get started. We have actually launched spacecraft that are beyond the edge of our solar system. Voyager 1, launched way back in 1977, is the most distant human-made object ever built. As of today, it is traveling away from us at roughly 17 kilometers per second. 17 kilometers every single second. That sounds fast. That is fast by any everyday standard. It's faster than most things you'll ever encounter in your lifetime, but here's where the universe humbles you. At that speed, Voyager 1 would take approximately 75,000 years to reach Proxima Centauri, if it were even headed in that direction, which it isn't. 75,000 years. Let that settle in for a moment. 75,000 years ago, modern humans were just beginning to leave Africa. We were painting on cave walls. We hadn't yet invented writing or agriculture or cities. And a spacecraft moving faster than almost anything we've ever built would still not have arrived at our closest stellar neighbor. That's how far away it is. That's how small we are in relation to even the most local corner of the cosmos. And yet, and this is the part that makes science so breathtaking, we haven't stopped trying to figure it out. We haven't shrugged and said too far doesn't matter. Instead, the smartest minds on Earth have been asking, what if we went faster? What if we went much faster? So let's talk about speed. Let's talk about the spacecraft we have right now, the concepts being actively developed, and the ideas that live just beyond the bleeding edge of what we currently know how to build. Right now, the fastest spacecraft humanity has ever launched is the Parker Solar Probe. It was designed to study our own sun, diving closer to it than any previous machine, and as a result of those close solar flybies, it accelerates to extraordinary speeds. At its fastest, it reaches roughly 700,000 kilometers per hour. That's about 0.067% the speed of light, which sounds tiny, but in human terms it's extraordinary. And yet, even at that incredible velocity, the Parker Solar Probe would take approximately 7,000 years to reach Proxima Centauri. 7,000 years. Gone from ancient Egypt to today is only about 5,000 years. 7,000 years of travel, and you'd still be arriving at the very first stop outside our solar system. So chemical rockets, the kind we've used since the dawn of the space age, the kind that burned kerosene and liquid oxygen to push Apollo astronauts toward the moon, those are completely, fundamentally inadequate for interstellar travel. They get us around our own solar neighborhood just fine. But against the scale of interstellar space, they are like trying to cross an ocean in a rowboat. We need something different, something radically, conceptually different, and that's where things get genuinely exciting. Because scientists and engineers aren't just dreaming in the abstract. They are working on real proposals, real physics, real experiments, and some of these ideas are not as far away as you might think. Here's something worth pausing on before we go deeper into the science. You know what makes the question of reaching Proxima Centauri even more fascinating? It's not just the distance, it's what might be waiting for us there. Because Proxima Centauri, that faint red dwarf 4-ish light-years away, has planets. In 2016, astronomers at the European Southern Observatory announced the discovery of a planet orbiting Proxima Centauri. They called it Proxima Centauri b. It's roughly Earth-sized, maybe 1.1 times our planet's mass, and it orbits within what scientists call the habitable zone. That's the region around a star where temperatures might, under the right conditions, allow liquid water to exist on a surface. an orbit so tight that a year on Proxima b lasts only about 11.2 days. Since then, researchers have found evidence of additional worlds. A sub-Earth called Proxima d orbiting even closer, and a candidate planet farther out. Our nearest stellar neighbor might not be a dead system. It might be a planetary system. One that, however harsh and strange, raises the oldest question in human consciousness. Are we alone? That's the destination. That's what's at stake. And that's why the question of how long it would take to get there matters so much more than just numbers on a page. Speaking of what might be waiting and what it would take to survive the journey itself, I actually made a separate video that goes deep into the physical and biological nightmare of traveling through interstellar space. It's called Why Surviving Interstellar Space is Worse Than Reaching It, and honestly, once you finish this one, that video is the perfect next chapter. The distance is one problem. Staying alive through it? That's a whole other level of terrifying and fascinating. I'll link it for you. Now, back to the question of speed, back to the science of getting there. The most talked about serious proposal in recent years came in 2016, when physicist and entrepreneur Yuri Milner, alongside the late Stephen Hawking and a team of leading scientists, announced a project called Breakthrough Starshot. The concept was bold, almost audacious in its simplicity. You don't send a large spacecraft. You send something tiny, a nanocraft weighing just a few grams, no heavier than a paperclip. You attach an ultra-thin sail, just a few meters wide, made of the most lightweight materials imaginable. And then you hit it with a focused array of ground-based lasers pumping up to 100 gigawatts of power. For about 10 minutes, those lasers push the nanocraft to roughly 20% the speed of light. 20% of 300,000 kilometers per second. That's 60,000 kilometers every single second. At that speed, the journey to Proxima Centauri would take somewhere around 20 to 25 years, not 75,000, not 7,020, within a human lifetime, within the career of a scientist who starts working on the project today. That idea changed the conversation about interstellar travel. It made something that had always felt like mythology feel like engineering. And the research that followed, on sail materials, laser systems, miniaturized spacecraft, produced genuinely novel science. As recently as January 2025, researchers at Caltech published work in the journal Nature Photonics documenting the first direct measurements of radiation pressure on a prototype light sail material made of silicon nitride just 50 nanometers thick. The physics works. The engineering challenges are enormous, almost absurdly so, and as of 2025, the Breakthrough Starshot project has been quietly put on hold, its funding far below what was originally promised. The dream didn't die, but it ran into the very human problem of turning visionary ideas into sustained, funded, real-world programs. But here's what's important. The questions it raised don't go away. The door it opened doesn't close. And the underlying physics, laser propulsion, light sails, miniaturized interstellar probes, those fields continue to grow, pushed forward by researchers who refuse to accept that the stars are out of reach. We are just getting started. Coming up, nuclear propulsion concepts that could cut the trip down to a matter of decades, the strange physics of what happens to time when you travel close to the speed of light, the almost unimaginable engineering of a multi-generational mission, and the deeper question that underlies all of this, not just can we get there, but why does it matter that we even try? Stay with me. Let's talk about fire, not the kind you light in a fireplace, not even the kind that roared beneath the Saturn V rocket that carried Apollo 11 to the moon. We're talking about a fundamentally different category of fire, one that burns not through chemistry, but through the raw energy locked inside the nucleus of an atom itself. Because if we're serious about reaching Proxima Centauri in a time frame that means something to human civilization, not 75,000 years, not 7,000, but something closer to a human lifetime or a few generations, then chemical propulsion isn't even part of the conversation. We have to go nuclear. And before that word makes you nervous, let me reframe it. Nuclear energy, in the context of space propulsion, isn't about bombs or danger in the way we typically imagine. It's about one of the most elegant facts in all of physics, that matter itself is frozen energy, that the nucleus of an atom contains an almost incomprehensible amount of power, and that if you know how to unlock it, through fission, splitting atoms apart, or fusion, pressing them together, you access energy densities that dwarf anything chemistry can offer by factors of millions. That's the key to interstellar travel. Not bigger rockets, not more fuel. A fundamentally different source of energy. The idea of nuclear-powered spacecraft is older than most people realize. Back in the 1950s and 60s, during the early space race, the United States ran a program called Project Orion, not the capsule we use today, but a completely different, almost science-fictional concept. The idea was to propel a spacecraft by detonating a series of small nuclear bombs behind it. Each explosion would push against a massive shock-absorbing plate, nudging the ship forward. Repeatedly, hundreds or even thousands of times. It sounds insane, and in some ways it was. The engineering was genuinely brilliant. Freeman Dyson, one of the most creative physicists of the 20th century, worked on it and believed it could work. Studies suggested that an Orion-type spacecraft could reach speeds of about 3 to 5% the speed of light. At 3% the speed of light, you're looking at roughly 140 years to reach Proxima Centauri. At 5%, closer to 85 years. Still a long time, but not geological time, not the age of civilization, a few generations. The kind of timescale that humans have operated on before. Think of the centuries it took to build the great cathedrals of Europe, planned and started by people who knew they would never see them finished, yet built them anyway. Project Orion was ultimately cancelled, not because the physics didn't work, but because the Partial Nuclear Test Ban Treaty of 1963 made it illegal to detonate nuclear devices in space, a political and environmental decision, not a scientific one. The concept was shelved, and with it, one of the most ambitious propulsion ideas ever seriously considered. But the dream didn't stay dormant. In the 1970s, the British Interplanetary Society, a real organization, one of the oldest and most respected in the field, launched a 5-year study called Project Daedalus. This was a serious peer-reviewed engineering effort, not science fiction. A team of scientists and engineers attempted to design from first principles a fusion-powered spacecraft that could reach Barnard's star, about 6 light-years away, within 50 years of launch. The design they came up with was staggering. A 2-stage spacecraft weighing around 50,000 metric tons at launch, the vast majority of that being fuel. The propulsion system would work by firing tiny pellets of deuterium and helium-3 into a reaction chamber, triggering microfusion explosions 250 times per second. Each tiny explosion would add to a continuous thrust, pushing the ship to roughly 12% the speed of light, 12% of light speed. That's about 36,000 kilometers per second. At that velocity, a journey to Proxima Centauri, closer than Barnard's star, would take roughly 36 years, about the time it takes to go from being born to approaching middle age. Project Daedalus was never meant to be a blueprint ready for immediate construction. It was a proof of concept, a demonstration that the physics allowed for interstellar travel within human timescales, and it succeeded in that mission. It showed the scientific community that interstellar flight wasn't magic or fantasy. It was engineering, brutally hard engineering, yes, but engineering nonetheless. Then, in 2009, the British Interplanetary Society launched a follow-up study, Project Icarus, named after the figure from Greek mythology who flew too close to the sun, perhaps a deliberate reminder that ambition must be tempered with wisdom. Icarus was designed to revisit and improve on Daedalus using 4 more decades of scientific knowledge. The Icarus team has explored multiple configurations, fuel types and mission profiles. Some variants aim for Proxima Centauri specifically. The designs vary in their details, but the general target remains: a fusion-powered craft reaching somewhere between 10 and 20% the speed of light, delivering a probe, or at least a stream of data, to another star system within the span of a human lifetime. One of the key problems Icarus identified was fuel. Project Daedalus relied heavily on helium-3, a rare isotope that barely exists in Earth's atmosphere, but is thought to be far more abundant in the atmosphere of the outer gas giants, particularly Uranus and Neptune. So one vision of interstellar civilization looks something like this. First, we establish infrastructure in the outer solar system. We mine helium-3 from ice giants, we refine it. We use it to fuel the engines of a starship, and then we launch. That's not a plan for next year, but it might be a plan for the next 200 years, and on the cosmic timescale, 200 years is nothing, less than a breath. There's another concept worth knowing about, because it keeps coming up in serious scientific discussions: the fusion ramjet, also called the Bussard ram scoop. Proposed by physicist Robert Bussard in 1960, the idea is elegant to the point of being almost poetic. Instead of carrying all your fuel with you, which is the fundamental problem of every rocket, the reason spacecraft are mostly fueled by mass. What if you scooped your fuel from the interstellar medium as you traveled? Space isn't perfectly empty. There are hydrogen atoms drifting between the stars, 1 or 2 per cubic centimeter on average. The ramjet concept imagines a magnetic funnel stretching out in front of a spacecraft, enormous, perhaps thousands of kilometers across, gathering those hydrogen atoms and funneling them into a fusion reactor, which then burns the hydrogen and expels the exhaust to generate thrust. In theory, this gets more efficient the faster you go. You travel faster, you scoop more, you generate more thrust. In theory, you could accelerate continuously, indefinitely, approaching the speed of light over long enough time frames. There's a catch. Several, actually. Later analyses revealed that the interstellar medium is too sparse and too full of the wrong types of hydrogen, mostly neutral atoms that are almost impossible to scoop magnetically. The drag caused by scooping might actually exceed the thrust generated, and the engineering of a magnetic funnel operating at those scales is, to put it mildly, beyond anything we currently understand how to build. But here's the thing about the Bussard ramjet. Even if the original design doesn't work, the idea it represents is still alive. The idea that a spacecraft could feed itself from its environment, that you don't necessarily need to carry all your energy with you. Variations and refinements of this concept continue to appear in the scientific literature, adapted to new understandings of the interstellar medium and new ideas about what kinds of fusion reactions might be practical. The universe, it turns out, is full of potential fuel. We just haven't figured out how to use it yet. Now, here's something important to hold on to as we walk through all of these propulsion concepts. Every single one of them, Orion, Daedalus, Icarus, the ramjet, shares a common feature. They require breakthroughs, not necessarily miraculous, impossible breakthroughs, but sustained, generational, civilizational investment in science and engineering. The kind of effort we put into the Manhattan Project or the Apollo program, but stretched over decades or centuries rather than years. We live in a world where funding for fundamental science is fragile, where long-term thinking is rare, where the distance between a brilliant idea and a working spacecraft is filled with budget cycles and political will and public interest. And yet, every generation of scientists who has looked seriously at this problem has come back with the same conclusion. It's not impossible. The physics permits it. The universe hasn't written any laws that say humans cannot reach the stars. The barriers are engineering and economics and time, and those, unlike the laws of physics, are things we have some control over. That's not naive optimism. That's what the math says. But there's a dimension to this journey that we haven't touched yet, one that bends your sense of reality in the most profound way. Because when you start moving at a significant fraction of the speed of light, something deeply strange begins to happen. Not just to your spacecraft, not just to the physics of your engines, but to time itself. Einstein showed us this, and it's not metaphor, it's not philosophy. It's one of the most rigorously tested, experimentally confirmed facts in all of science. Time slows down when you move fast. At 20% the speed of light, the target speed of breakthrough Starshot's tiny nanocraft, the effect is relatively small. But as you push toward 50, 60, 70, 80% of light speed, it becomes significant. At 99% the speed of light, time on your spacecraft would pass at roughly 1/7 the rate of time on Earth, which means the question, how long does it take to reach Proxima Centauri, actually has two very different answers, depending on who you're asking it to. That's where we're headed next. Part 3 is going to crack open the strangeness of relativistic time, what Einstein's special relativity means for the crew of an interstellar ship, what it means for the people they leave behind, and how a journey that takes 20 years by one clock might take a completely different span by another. It's one of the most mind-bending corners of physics, and I think you're going to love it. Let's talk about time, not in the way we usually talk about it, as a river flowing in one direction, steady and reliable, the same for everyone everywhere. That version of time is intuitive. It's the one your body knows, it's the one your watch keeps, it's the one that tells you when to wake up, when to eat, when to sleep. But it's not the whole truth. The full truth is stranger, more beautiful, more unsettling, and it was laid out in extraordinary detail by a 26-year-old patent clerk in Bern, Switzerland, in the year 1905. His name, of course, was Albert Einstein, and what he proposed in his special theory of relativity didn't just change physics. It changed the nature of reality itself. The core idea, stripped down to its most essential form, is this: the speed of light is constant, always, for everyone, regardless of how fast the observer is moving. Light travels at roughly 299,792 kilometers per second in a vacuum, and nothing in the universe observes it moving at any other speed. That sounds simple, but pull on that thread and everything unravels, because if light is always constant, and if speed is defined as distance divided by time, then for light to appear the same speed to two observers moving relative to each other, something else has to change. Distance can compress. And time can stretch. This isn't an abstract idea. It isn't a thought experiment with no real-world consequences. It has been measured, confirmed, verified in particle accelerators, in atomic clocks flown on airplanes, in GPS satellites, whose timing systems would fail within minutes if engineers didn't account for relativistic effects. The physics is real. The strangeness is real. And for an interstellar traveler, it becomes the most personal fact in the universe. Here's how time dilation works in practice. Imagine you board a spacecraft, sleek, impossibly advanced, humming with the output of a fusion reactor, and you accelerate away from Earth toward Proxima Centauri. As your speed increases, something begins to happen to time aboard your ship. From the perspective of someone watching you from Earth, your clocks tick slower, your heartbeat slows. Every process, biological, mechanical, atomic, runs at a reduced rate compared to what's happening back home. The faster you go, the stronger the effect. At 10% the speed of light, the difference is small, barely measurable in human terms over a short trip. But as you push higher, the numbers become dramatic. At 86.6% the speed of light, time on your ship runs at exactly half the rate it does on Earth. For every 2 years that pass on Earth, only 1 year passes for you. At 99% the speed of light, that factor of compression jumps to roughly 7. Every 7 years on Earth you experience 1. At 99.9%, the factor is about 22. Every 22 years on Earth, 1 year for you. Plil it even further, and the numbers become almost surreal. At 99.999% of light speed, time aboard your vessel runs more than 700 times slower than on Earth. Now let's apply this to Proxima Centauri. The star sits 4.24 light-years away. If you could somehow travel at exactly the speed of light, which you can't, because physics forbids any object with mass from actually reaching it, only approaching it asymptotically, the journey would take 4.24 years as measured from Earth. But due to time dilation at light speed being theoretically infinite, the crew would experience zero time, a flash, an instant. In reality, let's think about something more physically achievable. Imagine a spacecraft that could accelerate at 1 g, the same gravitational pull you feel standing on Earth, one standard gravity, continuously, first accelerating for the first half of the journey, then flipping and decelerating for the second half to arrive softly. This is a concept engineers and physicists have explored at length. Because continuous 1 g acceleration is deeply appealing, it would provide a sense of normal gravity for the crew the entire time, solving one of the major health challenges of long-duration spaceflight. At a constant 1 g acceleration and deceleration profile, a spacecraft would reach Proxima Centauri in about 3.6 years as measured from Earth. But for the crew on board, thanks to time dilation, the experienced journey time would be closer to 3.5 years, nearly the same at this relatively modest final velocity. But here's where it gets profound. Push that same 1 g ship further. Send it to the center of our galaxy, 26,000 light-years away. Earth time for that trip, about 26,000 years. Crew time, thanks to time dilation, roughly 20 years. A single human lifetime to cross the entire width of our galaxy. The universe permits this. The mathematics allows it. The energy required is extraordinary, almost incomprehensible by current standards, but there is no physical law that forbids it. This phenomenon has a name when applied to the comparison between two people experiencing different rates of time. It's called the twin paradox. Imagine two identical twins born on the same day. One stays on Earth. One boards an interstellar ship and travels to Proxima Centauri and back at a high fraction of the speed of light. When the traveling twin returns, they are younger than the twin who stayed. Not metaphorically, not in terms of how they feel. Actually, physically, measurably younger. Their cells have divided fewer times. Their telomeres are longer. Their biological clock genuinely ran slower during the journey. It's called a paradox because at first glance it seems contradictory. If motion is relative, why isn't each twin equally young from the other's perspective? The resolution lies in the fact that the traveling twin underwent acceleration and deceleration, changes in velocity, while the Earth twin did not. The experience is not symmetrical. The asymmetry resolves the paradox, and the result stands. Relativistic travel is, in a very real sense, a form of time travel into the future. You leave Earth, you travel to the stars, you come back. And the world you return to may be decades or centuries older than the one you left. While you have aged only a fraction of that time, let's sit with what that actually means for a moment. You leave behind your friends, your family, everyone you love. You travel for, let's say, from your own experience, 3 years. You arrive at Proxima Centauri, orbit its planets, gather data, maybe even land. You spend a year there. you travel 3 years back. From your perspective, 7 years of your life, 7 years of experiences, growth, memory, you return to Earth, and 8 or 9 years have passed there too, roughly, at the velocities we've been discussing. So far, so manageable, but push the speed higher, and the gap widens into something heartbreaking. Travel at 90% the speed of light, and the travelers age roughly 4 years on the round trip to Proxima Centauri and back, while nearly 9 years pass on Earth. Still survivable, you'd likely return to find an Earth changed, but not alien to you. Now imagine traveling to a star 20 light-years away at that same speed. You age about 25 years, Earth ages 43. You come back to find your children middle-aged, your peers elderly or gone. The stars are accessible, but they come with a cost that isn't measured in fuel or engineering. It's measured in the people you leave behind, in the irreversible separation of shared time. That is one of the most profound emotional truths of interstellar travel, and it's one that science fiction has explored endlessly, but that hard physics makes real. Now here is something that doesn't get discussed enough in popular science. The fact that time dilation cuts both ways in terms of planning. From a mission design perspective, relativistic time dilation is actually an advantage. It means that for the crew, the journey feels shorter than it looks on paper. A trip that takes 40 years from Earth's perspective might only feel like 20 from inside the ship. That has real implications for life support, psychological health, food, aging, morale. Shorter experience time means less resource consumption, less psychological strain, less biological degradation, but it also creates a communication nightmare. As a ship accelerates to significant fractions of light speed, signals sent from Earth take longer and longer to arrive, not just because of the distance, but because of the compounding effects of relativistic Doppler shift. Messages become stretched, slowed, distorted. The crew and Earth are not just physically separated, they are temporally separated, living in different rhythms of time, sending letters across an ever-widening gap that light itself struggles to bridge in useful time. Any mission to another star would need to grapple with this from day one. Mission control on Earth would be making decisions based on information that is years out of date. The crew would be responding to instructions that were sent years before they arrived. At some point, the ship has to be autonomous. The crew has to be capable of making every decision themselves, with no meaningful possibility of real-time guidance from home. That's not just a technical challenge. That's a psychological and philosophical one. A crew traveling to another star would be, in a very deep sense, on their own, more alone than any human beings in history, farther from help than any explorer who ever drew breath. And yet, here is the thing that never ceases to move me about this entire field of inquiry. Humans have always stepped into that kind of solitude when the horizon called. The Polynesian navigators who crossed the Pacific in open outrigger canoes, without maps, guided only by stars and ocean swells, and inherited knowledge, didn't know what lay beyond the horizon. They went anyway. The first peoples to walk across the land bridges into unknown continents didn't have satellite images or survival manuals. They moved into the dark because curiosity and need and courage are among the oldest human traits. We are, at our core, a species that goes, and when you understand that, the interstellar problem shifts from being purely technical to being deeply, essentially human. The question isn't only whether we can build an engine fast enough, it's whether we are, as a species, the kind of beings who look at 4.24 light-years of darkness and decide that the journey is worth taking. Everything about our history suggests that the answer is yes. But even if we solve the propulsion problem, and even if we make peace with the strangeness of relativistic time, there's another scenario we haven't fully faced yet. What if the journey can't be shortened enough? What if the most realistic missions to Proxima Centauri Not nanocraft, not relativistic rockets, but large human-crewed ships. Take not 20 years, but 200. Not one lifetime, but several. What happens to a civilization that forms inside a spacecraft? What does it mean to be born, live, and die on a ship, never having seen the world you came from, never knowing whether you'll survive to see the world you're headed toward? That's the question waiting for us in Part 4. The multi-generational ship, the most human and the most heartbreaking solution to the interstellar distance problem. Don't go anywhere. We are just starting. Imagine being born on a ship, not visiting one, not working on one for a tour of duty before returning home, born on one, raised on one, growing up knowing that the walls around you are the entirety of your world, that outside those walls is a vacuum so hostile it would kill you in seconds, and that the closest star, the one you came from, is already years behind you, a point of light indistinguishable from the thousands of others scattered across the dark. You didn't choose this journey. It was chosen for you, by parents, by grandparents, by a civilization that looked at the stars and decided to reach for them before the technology to do it quickly existed. You are not the explorer. You are the middle chapter of a story that started before you were born and will end long after you die. This is the reality of what scientists and futurists call the generation ship, or the multi-generational vessel. And it is, without question, one of the most philosophically complex ideas in the entire history of human exploration. The concept is straightforward in its logic, even if it's staggering in its implications. If we cannot accelerate a crewed spacecraft fast enough to reach another star within a single human lifetime, then perhaps the answer is to bring the lifetime to the ship. To build a vessel large enough, self-sufficient enough, and stable enough to sustain not one generation of travelers, but many, 10, 20, perhaps 50 generations, across the centuries it takes to cross the interstellar gulf. At the speeds of our most advanced current spacecraft, the kind we could realistically build within the next century, before exotic propulsion becomes possible, a journey to Proxima Centauri might take somewhere between 500 and 1,000 years. That's a civilization in transit, an entire arc of human history, compressed into a metal shell moving through the void between stars. The idea has been taken seriously by serious people. Carl Sagan discussed it. Freeman Dyson explored its implications. The mathematician and physicist Krafft Ericka, one of the pioneers of early rocketry, wrote about it in technical terms in the 1960s. More recently, researchers at institutions from NASA to independent think tanks have attempted to calculate the minimum viable population for such a mission, the social structures that might sustain it, the genetic diversity required to prevent collapse over dozens of generations. This isn't science fiction dressed up in academic language. It's a genuine field of inquiry, because if humanity is ever going to become a truly interstellar species, not just sending probes but actually going, generation ships may be one of the most realistic near-term pathways. Let's start with the math, because the numbers are illuminating. A generation ship isn't a sleek needle hurtling through space, it's a world. To sustain a human population over centuries, you need food production, which means agriculture, which means land area, grow light, soil or hydroponic systems, water cycles, atmospheric regulation. You need manufacturing, tools wear out, systems fail, parts break. You need medicine, education, governance, culture, art. You need the full infrastructure of a functioning society, miniaturized and sealed inside a vessel that must operate without resupply for potentially 1,000 years. Studies on minimum viable population, the smallest number of people needed to maintain genetic diversity and social stability over many generations, have produced varying results. Some analyses suggest as few as 160 people could theoretically sustain a population if genetic diversity is carefully managed. Others argue that a more realistic and resilient minimum is closer to 10,000, accounting for disease, accident, social collapse, and the psychological needs of a healthy community. 10,000 people. Imagine the ship you'd need to build, the mass, the volume, the energy to propel it, the complexity of its life support systems. This isn't a spacecraft in any conventional sense. It's a small city, launched into permanent exile among the stars. Some concepts go further. The O'Neill cylinder, proposed by physicist Gerard O'Neill in the 1970s, describes a rotating cylindrical habitat large enough to house tens of thousands of people, with centrifugal force simulating gravity on the inner surface. Forests, rivers, towns, an artificial sky. These weren't proposed specifically for interstellar travel, but the concept scales, in theory. A sufficiently large O'Neill cylinder, given enough energy for propulsion, could serve as a generation ship that doesn't feel like a ship from the inside. It feels like home. But here is where the engineering problem fades and the human problem takes over, because building the ship is in some ways the easier part. The harder question is this: what happens to the people inside? The first generation, the ones who volunteered, who trained, who understood the mission, who made the choice. They have context, they have memory of Earth, they have the emotional fuel of having chosen this, of being the pioneers, the bold ones who said yes to the stars. Their commitment is deep because it's personal, it's theirs. The second generation grew up on the ship. They know Earth only through stories, videos, cultural memory. They didn't choose this voyage. They were born into it. Their relationship to the mission is inherited, not chosen. Research in social psychology and anthropology suggests that inherited identities are powerful. Think of national identity, religious tradition, cultural heritage, but they are also subject to drift, reinterpretation, and rejection. The second generation might embrace the mission with the fervor of the faithful, or they might begin to question it. By the 10th generation, the connection to Earth is historical, not personal, as distant as ancient Rome feels to us. The mission, reach a star 4 light-years away, might feel as abstract and inherited as a founding myth. And like all founding myths, it could inspire or it could hollow out. It could become the organizing purpose of a thriving community or a dogma enforced by authority on people who no longer feel it in their bones. By the 50th generation, if the ship hasn't arrived, the original mission documents might be artifacts in a museum, the founders, legendary figures, the destination, an article of faith. This is not speculation. We have real-world parallels, and they're instructive. Consider the experience of immigrant communities who moved across oceans in the age of sail, who left their home countries knowing they would never return, whose children grew up with dual identities, whose grandchildren sometimes barely spoke the ancestral language, whose great-grandchildren knew their origins only as family mythology. That drift happened over 2 or 3 generations, with constant communication back home, with cultural reinforcement through books and trade and occasional visitors. Now imagine that same drift, but with no communication home possible in real time, with no resupply ships, with no new immigrants arriving to refresh cultural memory. In complete isolation, the sociological challenge of a generation ship isn't just about keeping people fed and the air breathable. It's about maintaining coherent, functional civilization across the one condition human civilization has never before had to endure: true, total, permanent isolation, persisting across centuries. Some researchers have proposed strict cultural protocols, detailed records, rituals, educational requirements designed to transmit mission identity across generations the way religious traditions transmit belief. Others have suggested that attempting to freeze the culture of the founding generation is not only futile but dangerous, that a healthy shipboard society would need to evolve organically, adapting its governance, its values, its relationship to the mission as circumstances changed. There is a deep tension here. Too rigid, and the ship becomes a totalitarian state, a closed world where dissent is existential threat, where the children of dissenters have nowhere to go, no exit, no escape. Too flexible, and mission coherence might dissolve. A generation might arise that abandons the destination entirely, choosing to live indefinitely in transit rather than risk the unknown of arrival. There's a specific thought experiment in this space that I find genuinely haunting. It's sometimes called the Mayflower problem, named after the ship that carried the pilgrims to the New World. On the Mayflower, everyone on board had chosen to be there, shared a common purpose, and knew the journey would end in weeks. Even then, by the time they arrived, there was significant internal conflict about leadership, governance, and what the rules would be in the new land. The Mayflower Compact, one of the earliest documents of democratic governance in American history, was written essentially to prevent mutiny during the final days of the crossing. Now scale that to centuries, to people who were born on the ship without choosing it, to a destination that has become myth rather than plan, to a governance structure that must remain functional across generations without any external enforcement or legitimacy derived from a home culture. What keeps people working toward the mission? What prevents a faction from seizing control of the navigation systems and simply stopping, drifting in space forever, neither going forward nor back? What happens when people fall in love with the ship, with the only world they've ever known, and resist arrival at a destination that will mean the end of everything familiar to them? These are not trivial questions. They are the kind of questions that civilizations have answered and failed to answer throughout history. And on a generation ship, failure isn't a historical tragedy to be studied later. It's extinction. And yet, and this is the part that always pulls me back from the edge of despair and into something like wonder, human beings have built and sustained extraordinary institutions across long timescales before. Not perfectly, not without crisis and regression and periods of dark, but we have done it. The Catholic Church has maintained organizational continuity for over 2,000 years. The Chinese imperial examination system ran, with interruptions, for roughly 1,300 years. Indigenous oral traditions carried detailed ecological and astronomical knowledge across hundreds of generations without writing. The human capacity for institutional memory, for transmitting purpose and meaning across time, is genuinely remarkable. A generation ship would need to tap that capacity in a focused, intentional, engineered way. It would be, in a sense, the most deliberately designed civilization in human history. Every institution, every tradition, every cultural practice, chosen not organically, but with a specific multi-generational purpose in mind. That's terrifying, and it's also, in its own strange way, beautiful, the most intentional act of civilization building ever attempted. There is one more dimension to this that science is only beginning to grapple with seriously: the biology. Human genetics don't stand still over centuries. With a small founding population, the risks of genetic bottlenecking are real. Reduced diversity leading to increased expression of recessive traits, reduced immune resilience, reduced adaptability. To counter this, mission designers have proposed everything from carefully curated genetic databases to allow for artificial insemination with diverse donor material to the possibility of, and this takes us into genuinely new scientific territory, synthesizing gametes, sperm and eggs, from stored genetic material, allowing future generations to reproduce with the effective genetic contribution of thousands of people who never set foot on the ship. The science of synthetic gametes is real and advancing. It has been demonstrated in mice. Human applications are not imminent, but they are not fantastical either. Within a century, The technology may exist to allow the generation ship to carry the genetic heritage of millions of people in a storage drive and use that heritage to maintain diversity across the entire voyage, which raises a question that is simultaneously biological, ethical, and profoundly human. What does it mean to be the ancestor of someone you never knew, who was born centuries after you on a ship you never boarded, on the way to a star you'll never see? What kind of inheritance is that? The same kind, perhaps, that every human who ever planted a tree they wouldn't live to sit under has always given. The kind that says, "I did this for you, even though I'll never know your name. Let's talk about where we're actually going, because everything we've discussed so far, the engines, the timescales, the relativistic strangeness, the multi-generational civilizations in transit, all of it has been about the journey, the how, the cost, the sacrifice. But there's a question sitting quietly underneath all of that, one that every serious scientist in this field carries with them, one that changes the entire emotional weight of the conversation. What's there when we arrive? Is Proxima Centauri a destination worth the impossible effort of reaching it? Or is it a cold, barren, radiation-scorched system with no atmosphere, no liquid water, no chemistry of life, a monument to the cruelty of cosmic distance, offering nothing to justify the centuries of sacrifice it took to cross it? This is not an abstract question anymore. We have data, real data, gathered by real telescopes, analyzed by real scientists who have spent careers trying to understand what orbits our near-stellar neighbor, and what they've found is complicated, fascinating, frustrating in exactly the way that frontier science always is, and, depending on how you read it, quietly breathtaking. Let's start with what we know. Proxima Centauri is a red dwarf star. Specifically, it's an M-type main sequence star, the most common type of star in the Milky Way. More than 70% of all stars in our galaxy are red dwarfs. So in a very real sense, when we look at Proxima, we're not looking at something exotic or unusual. We're looking at the most typical kind of star the galaxy produces. But typical doesn't mean simple. Red dwarfs are smaller, cooler, and far dimmer than our Sun. Proxima Centauri has about 12% of the Sun's mass, and its surface temperature is roughly 3,000 degrees Celsius, compared to about 5,500 for the Sun. It burns its fuel so slowly and so efficiently that it will remain in this phase of its life for roughly 4 trillion years. For context, the current age of the universe is about 13.8 billion years. Our Sun will exhaust its hydrogen fuel in roughly another 5 billion years. Proxima Centauri will be quietly burning long after every Sun-like star in the observable universe has died. In terms of raw longevity, it is one of the most enduring objects in the cosmos. But there is a dark side to the red dwarf story, and it's the thing that makes astrobiologists lose sleep. Red dwarfs are violent, not continuously, not in the way a massive blue star blazes with ferocious intensity, but sporadically, unpredictably, and in a way that poses an existential threat to anything trying to live in their vicinity. They flare. Proxima Centauri is what astronomers classify as a flare star, meaning it regularly produces intense bursts of ultraviolet and X-ray radiation, sudden releases of magnetic energy that dwarf anything our Sun produces in its most intense solar storms. In May of 2019, astronomers using the Atacama Large Millimeter Array, ALMA, recorded a flare from Proxima Centauri that was roughly 1,000 times brighter than any flare ever recorded from our Sun. It lasted only a few seconds, but in those few seconds, it released enough radiation to potentially strip the atmosphere from any planet sitting in the habitable zone. Let's dwell on that for a moment, because this is the central tension of the Proxima Centauri story. On one hand, the system has planets in the right orbital range for liquid water. On the other hand, the star itself is a radiation cannon that fires without warning. The question, and it's a genuinely open one in current science, is whether those two facts are compatible with life or whether they're mutually exclusive. Here's where the story gets layered. In 2016, a team of astronomers using the HARP spectrograph at the European Southern Observatory confirmed the existence of a planet orbiting Proxima Centauri in its habitable zone. They called it Proxima Centauri b, and the announcement sent ripples through the scientific community that are still expanding today. Proxima b orbits its star at a distance of about 0.05 astronomical units, dramatically closer than Earth orbits our Sun. But because Proxima Centauri is so much dimmer and cooler, that close-in orbit places Proxima b right in the zone where temperatures could, under the right conditions, allow liquid water on the surface. It has an estimated minimum mass of about 1.17 times Earth's mass, which makes it likely a rocky planet, not a gas giant, not an ice planet, but something potentially Earth-like in its basic composition. Those facts alone were enough to make headlines around the world. Our nearest stellar neighbor has a rocky planet in the habitable zone. Let that land. But, and science is always full of buts, habitability is not just about distance from a star. It's about magnetic fields, atmospheric retention, water inventory, geological activity, tidal forces, and a dozen other factors that we simply don't yet know for Proxima b. One of the biggest concerns is tidal locking. At that orbital distance, Proxima b is almost certainly tidally locked to its star, the same way our moon is locked to Earth, always showing the same face. One side of the planet would be in permanent daylight, baking under the star's heat. The other side in permanent darkness, frozen. Whether the atmospheric dynamics of such a world could redistribute heat effectively enough to maintain habitable conditions on the terminator, the ring between day and night, is something climate models give mixed answers on. Some say yes, some say the atmosphere itself would freeze out on the night side and collapse. The truth is we don't know yet, and then there's the radiation. Even if Proxima b has an atmosphere, the stellar flares we've measured suggest a punishing radiation environment. For surface life, as we understand it, that's a serious problem. But, and here's where critical thinking matters, life is not limited to surfaces. Earth's oceans buffer radiation effectively. Underground environments are shielded. Life on Earth evolved in the oceans long before it colonized land, partly because water is an excellent radiation shield. A planet with liquid water oceans, even under a flare star, might harbor life in those oceans that never needs to interact with the surface environment at all. Microbial life in deep ocean hydrothermal systems on Earth exists without sunlight, without interacting with the atmosphere, sustained entirely by chemical energy from the planet's interior. If that kind of life can thrive here, the logic of biochemistry doesn't obviously forbid it elsewhere. This is exactly why astrobiology is one of the most exciting scientific fields alive right now. The more we learn about life on Earth, its range, its resilience, its capacity to colonize environments we once considered dead zones, the more possible life elsewhere becomes. In 2020, a second candidate planet was proposed in the Proxima Centauri system. Designated Proxima c, this one orbits much further out, at about 1.5 astronomical units, well outside the habitable zone, and appears to have a mass several times Earth's, suggesting it might be a super-Earth or a mini-Neptune. Its existence remains debated in the scientific literature, but multiple teams have attempted to confirm it using both radial velocity data and direct imaging, with the latter being extraordinarily difficult at this distance. Then in 2022, analysis of espresso spectrograph data, espresso being an even more precise instrument than HARPS, also at the European Southern Observatory, suggested the existence of yet another candidate, Proxima d. This one orbits even closer to the star than Proxima b, with a mass estimated at roughly a quarter of Earth's mass, making it one of the lightest exoplanets ever detected by the radial velocity method. Its confirmation is still pending, and it almost certainly lies inside the habitable zone's inner edge, likely too hot for liquid water. What this gives us is the emerging picture of a multi-planet system around Proxima Centauri. Not just one world, but potentially three, a complex, layered solar system orbiting the star next door. Now, and I want to pause here for just a second, because what I'm about to say matters to me personally, and I think it'll matter to you too. We are living in a genuinely extraordinary moment in the history of human knowledge. The confirmed detection of Proxima b happened less than a decade ago. The candidate detections of Proxima c and d are even more recent. The telescopes and spectrographs doing this work, HARPS, ESPRESSO, ALMA, represent decades of international scientific collaboration, billions in investment, and the labor of thousands of researchers across multiple generations. And we are, right now, at the very beginning of being able to characterize these worlds. The James Webb Space Telescope, launched in December of 2021, and now operating at the second Lagrange point, about 1.5 million kilometers from Earth, was not primarily designed for direct imaging of Proxima b. The star is too close and too bright relative to the planet for Webb's current capabilities. But next-generation observatories being planned and designed right now, including the extremely large telescope being built in Chile's Atacama Desert, expected to see first light in the late 2020s, may be capable of directly imaging Proxima b and analyzing its atmosphere through spectroscopy. That means within your lifetime, possibly within the next decade or two, we may know whether Proxima b has an atmosphere. We may know what that atmosphere is made of. We may find biosignatures, oxygen, methane, water vapor in combinations that chemistry alone can't easily explain, combinations that whisper of biological processes. We might, in short, find out that we are not alone. If that happens, if the spectrum of Proxima b's atmosphere comes back with the fingerprints of life, then every conversation about generation ships and nuclear propulsion and time dilation transforms instantly. It stops being a question of whether the journey is worth it and becomes a question of how fast we can possibly go. This is the kind of science that deserves an audience that actually cares. That's paying attention. That understands what's at stake, and if you've made it this far into this video, you're clearly that kind of person, someone who looks at a star 4 light years away and feels something. Curiosity, awe, maybe even a quiet pull toward the horizon. If that's you, then subscribing to this channel is genuinely worth your time, because this is what we do here. We take the biggest, most mind-bending questions in science, and we work through them honestly, carefully, and with the kind of wonder they deserve. Every week, another frontier, every video, another reason to feel grateful that we live in a universe this extraordinary. Hit subscribe and don't miss what's coming next. This community is growing, and I think you'll want to be part of where it's going. Now, back to Proxima b, because there's one more dimension to the habitability question that I haven't mentioned yet, one that researchers have started taking seriously only in the last few years, and that quietly shifts the odds in a more hopeful direction: magnetic fields. For a long time, the assumption was that a tidally locked planet around a red dwarf would likely have a weak or absent magnetic field, because magnetic field generation in rocky planets is linked to a planet's rotation rate and its internal heat. A tidally locked planet rotates very slowly relative to its star, once per orbit, which could mean insufficient internal dynamo activity to generate a protective magnetosphere. But more recent modeling work has challenged that assumption. Some studies suggest that the tidal forces from the star itself might generate enough internal heating through tidal flexing of the planet's interior to sustain geological activity and potentially a magnetic dynamo. The jury is still out, But the point is that we're learning. The picture is becoming more nuanced. The simple story of red dwarfs are too violent, forget it, is giving way to something more complex, more conditional, and in some ways more hopeful. The universe, as always, is more interesting than our first draft of understanding it. And speaking of more interesting than expected, there's an aspect of the Proxima Centauri system that almost nobody talks about, but that adds an extraordinary layer to this entire story. Proxima Centauri is not alone, it is gravitationally bound, loosely at an enormous distance, to a binary star system, Alpha Centauri A and Alpha Centauri B. These two stars orbit each other at a distance of roughly 11 to 36 astronomical units, completing one orbit around their common center of mass every about 79 years. And the whole Alpha Centauri system, A, B, and Proxima, forms a gravitationally associated triple star system, the closest stellar grouping to our own Sun. Alpha Centauri A is remarkably similar to our Sun, a G-type main sequence star with about 1.1 solar masses and a surface temperature within a few hundred degrees of our own star. Alpha Centauri B is slightly smaller and cooler, a K-type star, and in 2012, a team announced the detection of a planet candidate around Alpha Centauri B, though that detection was later disputed and largely retracted due to signal artifacts in the data. But the Alpha Centauri system remains a tantalizing target. ESA's CHEOPS mission and several ground-based programs are actively searching for planets around both Alpha Centauri A and B, and the Breakthrough Watch initiative, a companion program to Breakthrough Starshot, is specifically developing technology to directly image potentially habitable planets in the Alpha Centauri system. So when we talk about reaching Proxima Centauri, we're really talking about entering a three-star neighborhood, a system that contains, within its gravitational family, a Sun-like star, a slightly cooler companion, and a flare-prone red dwarf, each potentially harboring worlds, each posing different possibilities and challenges for life. The nearest star to us is not a single lonely point of light. It's a family, and we are only beginning to understand what it contains. Part 6 is going to pull back to look at something that reframes this entire conversation: artificial intelligence and autonomous probes. What if the first visitors to Proxima Centauri aren't biological at all? What if the first eyes that see those planets up close belong to a machine intelligence sophisticated enough to make decisions, conduct science, and transmit the story of what it found back to awaiting humanity? That future is closer than you think. Let's reset the frame for a moment. Everything we've talked about so far has assumed, at least implicitly, that the goal of reaching Proxima Centauri is ultimately about sending people, human beings, flesh and bone and consciousness, crossing 4.24 light-years of void to stand or float or crawl on another world and look up at an alien sky with their own eyes. That goal is real, it matters. There is something irreplaceable about the human presence in exploration, something that no instrument, no sensor, no data stream fully captures. When Neil Armstrong stepped onto the lunar surface, the moment wasn't significant because of the rock samples he collected. It was significant because a human being, a conscious, feeling, mortal creature, stood somewhere no human had ever stood and looked back at the world that made him. That matters. It will always matter. But here's the question that serious space scientists and mission planners are increasingly asking: does the first visit to another star have to be human? And is insisting on that, in fact, a kind of hubris that might delay us indefinitely, while a different approach could get us there within the lifetimes of people already alive today? The answer, emerging from the most forward-looking corners of aerospace engineering and artificial intelligence research, is quietly radical. The first emissaries to Proxima Centauri will almost certainly not be human. They will be machines, but not the dumb pre-programmed machines of the early space age. something fundamentally different, something that by the time it makes that journey may be capable of doing science, making decisions, adapting to the unexpected, and perhaps even, in some meaningful sense, experiencing the arrival. Let's ground this in what's actually happening right now, because the gap between current technology and what we're describing is smaller than most people realize. The field of autonomous spacecraft has been advancing rapidly for decades. NASA's Mars rovers, from Sojourner in 1997 to Spirit and Opportunity, to Curiosity, to Perseverance, represent a continuous evolution toward greater autonomy. Perseverance, which landed in Jezero crater in February of 2021, carries a level of onboard intelligence that would have seemed extraordinary to the engineers of the Viking program. It can autonomously navigate terrain, avoid obstacles, select scientifically interesting targets, and make real-time decisions about where to drive and what to study, all without waiting for instructions from Earth, which in any case arrive with a communications delay of between 3 and 22 minutes, depending on orbital geometry. The Ingenuity helicopter, the small rotorcraft that flew as a technology demonstrator alongside Perseverance, operated fully autonomously during each flight. It had to. The communication delay made real-time piloting impossible. Ingenuity planned its own flight path, adjusted to wind conditions, managed its own power, and reported back after the fact. Now scale that principle to interstellar distances. At Proxima Centauri, the communication delay isn't minutes, it's 4.24 years. Any probe arriving at that system is, by definition, completely on its own. There is no mission control it can call, no engineer it can ask, no software patch that can be uploaded in real time. Whatever intelligence it carries when it launches is what it has to work with, plus whatever it has learned and adapted along the way. This makes the artificial intelligence aboard an interstellar probe not a convenience or a feature. It's a fundamental requirement. The probe has to be capable of conducting an entire scientific mission autonomously, creatively, responsively, in an environment we have never visited, around a star we have never seen up close, encountering phenomena we cannot fully predict. And then it has to decide what data is worth compressing and transmitting home across more than 4 light-years of space, knowing that the signal will take years to arrive and that the humans who receive it may be living in a world significantly different from the one that launched the mission. Breakthrough Starshot, which we touched on in Part 1, gives us the most concrete current vision of what an autonomous interstellar probe might look like. The concept involves launching not one but potentially thousands of tiny spacecraft, each about the size of a postage stamp, called starships. Each starship would carry miniaturized cameras, communication lasers, power sources, and navigation systems, all packed onto a sail no thicker than a few hundred atoms, a light sail pushed by an enormously powerful ground-based laser array. The redundancy is deliberate. Interstellar space is not empty. It contains dust grains, high-energy particles, magnetic fields, and other hazards that could destroy a single fragile nanocraft. By launching thousands simultaneously, the mission accepts that many will be lost, while enough survive to return data. It's a strategy borrowed from biology, the same logic by which salmon release millions of eggs knowing that only a fraction will survive to adulthood. Each starship would carry its own miniaturized AI, not a general intelligence but a highly optimized system designed to navigate, collect data, prioritize observations, and transmit findings. The data compression alone is a remarkable challenge. Sending meaningful scientific information across 4 light-years using a laser the size that can fit on a postage stamp requires extraordinary efficiency in selecting what to send and how to encode it. The Breakthrough Starshot team, which includes some of the most eminent scientists and engineers alive, The late Stephen Hawking was among its founding advisors, alongside Yuri Milner and Avi Loeb of Harvard University, has identified the key engineering challenges and is actively working through them. The laser array, the light sail material, the miniaturization of instruments, the communication system, each is a significant unsolved problem, but none of them violate any known laws of physics. Now here is where artificial intelligence enters this story in a deeper way, not just as the onboard system of a nanocraft, but as the potential architect of the entire mission design. We are living through an extraordinary inflection point in the history of machine intelligence. Systems that can conduct scientific reasoning, generate hypotheses, analyze complex data, and communicate their findings in natural language exist today and are advancing rapidly. Within the time frame of a serious interstellar mission program, decades, not centuries, the question of what an AI system is capable of will look very different than it does right now. Imagine a probe launched not in the 2030s but in the 2080s or 2090s, after 50 more years of AI development. The intelligence aboard that craft might be capable of genuine scientific creativity, not just following a programmed observation sequence, but actually reasoning about what it observes, forming new hypotheses, designing follow-up observations in real time, and making judgment calls about what matters. It might be capable of recognizing biology if it encounters it, not just detecting specific pre-programmed chemical signatures, but reasoning about anomalies, patterns, and structures in ways that resemble how a human scientist thinks. Some researchers, including Avi Loeb, the Harvard astrophysicist who has been one of the most vocal advocates for ambitious interstellar science, have argued that the first truly capable interstellar probe should be thought of less like a camera on a stick and more like a robotic scientist, an entity that carries genuine intellectual capacity to the destination, conducts an open-ended investigation, and communicates not just raw data, but interpreted findings back to Earth. This is a profound shift in how we think about exploration. The history of robotic space exploration has been one of increasingly capable machines sent to increasingly challenging environments. The interstellar version of that trajectory leads somewhere that starts to blur the boundary between tool and explorer, and this raises a question that sounds philosophical but has genuine practical implications. If we send a sufficiently intelligent autonomous system to Proxima Centauri, and it spends 20 years traveling there, adapting and learning along the way, and then conducts years of independent scientific investigation in an alien star system, what is that system by the time it arrives? It launched as a machine built by humans. It arrives as something that has operated independently, without human oversight for decades. It has made thousands of decisions. It has processed an enormous amount of novel experience. It has, in whatever sense the word applies, a history. We don't need to answer the hard philosophical questions about machine consciousness to recognize that this is a genuinely new kind of entity in the history of exploration. Not a human explorer, not a dumb probe, something in between, or perhaps something entirely new, without a clean category. The scientists who think seriously about this don't dismiss it. They engage with it, because the design choices you make about an interstellar AI, how autonomous it should be, what values and priorities it should be given, how it should handle unexpected situations, whether it should be capable of revising its own mission parameters, are among the most consequential engineering decisions of the entire program. You are, in a meaningful sense, deciding what kind of mind first encounters another star system on behalf of humanity. That decision deserves thought. There is another approach to autonomous interstellar probes that sits further out on the technological horizon, but that serious scientists have written about in peer-reviewed literature. It's called the von Neumann probe concept, named after mathematician John von Neumann, who first formalized the idea of self-replicating machines. A von Neumann probe is a spacecraft designed not just to travel to another star and collect data, but to use resources it finds there, asteroids, moons, raw materials in the target system, to build copies of itself, which then travel to further stars and repeat the process. In principle, a single von Neumann probe launched from Earth could eventually lead to probes in every star system in the galaxy, spreading outward at a fraction of the speed of light in a wave of self-replicating explorers. The mathematics of exponential growth are staggering. Even traveling at 1% the speed of light, far slower than breakthrough Starshot, a self-replicating probe network could theoretically spread across the entire Milky Way in less than 10 million years, which is a long time in human terms, but less than 0.1% of the galaxy's age. Physicists including Frank Tipler and Carl Sagan have engaged seriously with this concept. It has implications not just for how we might explore the galaxy, but for a question that haunts astronomy. If intelligent life has existed elsewhere in the galaxy for billions of years before us, why don't we see evidence of von Neumann probes already here? Why hasn't the galaxy already been mapped by self-replicating machines launched by some earlier civilization? That question is one flavor of the Fermi paradox, the deep, unsettling silence of a universe that statistically should be teeming with intelligence, but observationally appears to show us none. And it's a question that, the more you dig into it, becomes one of the most important and disturbing puzzles in all of science. But we're not going to fully crack open the Fermi paradox today. That deserves its own dedicated exploration, and it's a road I want to take you down properly when we do. What I want to leave you with, at the end of this part, is a reframe of what reaching Proxima Centauri actually means in the context of autonomous probes and AI. The traditional image of interstellar arrival is a human crew stepping out of a spacecraft, planting a flag, breathing filtered alien air through a helmet, and looking up at two suns in an alien sky. That image is powerful, and maybe, one day, centuries from now, it will be real, but the first arrival will look different. It will be a swarm of postage stamp-sized light sails decelerating, or not, and simply flying through at 20% light speed, taking photographs and measurements in a brief, frantic window of close approach. Or it will be a more massive probe, slower but smarter, settling into orbit and beginning a patient, years-long investigation of a system it has traveled 2 decades to reach. Or it will be something we haven't imagined yet, built by an intelligence, human or artificial, that doesn't exist yet. In every case, the first data that comes back from another star system will change our civilization. Whatever those images show, a barren rockscape, a cloud-wrapped ocean world, a spectrum with the unmistakable signature of biological chemistry, nothing will be the same afterward. We will know for the first time what another star's planets actually look like up close. We will know whether our solar system is typical or exceptional. We will know, or begin to know, whether the universe made life once or many times. That knowledge is worth building toward, worth spending careers on, worth dreaming about in the dark. There is a photograph taken on February 14th, 1990 that I want you to think about. NASA's Voyager 1 spacecraft had just completed its primary mission, having visited Jupiter, Saturn, and their moons. It was nearly 6 billion kilometers from Earth, farther than any human-made object had ever traveled. Before its cameras were permanently switched off to conserve power, the mission team, led in part by Carl Sagan, who had advocated for years to make this image happen, commanded Voyager to turn around and photograph the inner solar system one last time. In the resulting image, Earth appears as a tiny point of light, less than a pixel across, suspended in a beam of scattered sunlight, pale, fragile, almost invisible against the vastness of space. Sagan called it the pale blue dot. And what he wrote about that image remains, in my view, one of the most important pieces of prose in the English language. He wrote, "Look again at that dot. That's here, that's home, that's us. On it, everyone you love, everyone you know, everyone you ever heard of, every human being who ever was, lived out their lives." That image and those words did something to the human imagination that no scientific paper ever could. They gave us perspective, not as an abstraction, but as a visceral, undeniable visual fact. We are small, our world is small, our conflicts, our borders, our certainties, all of them are taking place on a mote of dust suspended in a sunbeam. Now imagine what happens to the human imagination when the first image comes back from Proxima Centauri, when we see for the first time our own sun from another star's vantage point, a pale dot of our own, home from 4 light years away. What does that do to us? Throughout human history, every major expansion of our known world has changed us, not just technologically, not just economically, psychologically, philosophically, spiritually. When the first maps of the full globe were drawn, when European sailors returned with proof that the Earth was round and navigable, that there were continents and peoples and ecosystems no one in the known world had imagined. The effect was shattering and generative at the same time. It shattered the certainty of a fixed known world. It generated centuries of exploration, conflict, exchange, and eventually a slow and painful expansion of what we meant by the word humanity. When Copernicus and Galileo demonstrated that the Earth was not the center of the universe, that we orbited the Sun, which was itself one of countless stars, the psychological disruption was profound enough that it threatened the institutional foundations of an entire civilization. People didn't just update their astronomical models, they had to renegotiate their sense of cosmic significance, their place in the story. When Darwin showed that humans were not separately created, but were continuous with all other life on Earth, that we were cousins of every creature that ever lived on this planet, it was again not just a biological revision, but an identity earthquake, one we are in some ways still processing. Each of these moments, the round Earth, the heliocentric universe, the evolutionary origin of life, is what historians of science call a Copernican moment, a shift so fundamental that it doesn't just add to human knowledge. It restructures the framework within which all knowledge is understood. Becoming an interstellar species would be the next Copernican moment, and it would be bigger than all the previous ones combined. Think about what changes when we are no longer a single planet, single star civilization. The first and most obvious thing is the existential risk calculation. Right now, every human being who has ever lived, and every human being alive today, is dependent on a single planet orbiting a single star. Every catastrophe that could threaten Earth, an asteroid impact, a supervolcano, a runaway climate shift, a pandemic, a nuclear exchange, is a potential extinction event for our entire species. We have no backup, no redundancy. We are, in the language of risk management, catastrophically concentrated, an interstellar civilization, even a nascent one, even one with only a handful of settlements beyond our solar system, changes that equation fundamentally. A civilization spread across multiple star systems cannot be wiped out by a single event, no matter how catastrophic. The seeds of human consciousness, human culture, human biology would be distributed across light years of space, protected by the very distances that make interstellar travel so hard. This is not a cold actuarial argument, it's a moral one. Every generation that passes without us becoming multistellar is a generation in which the entire human story remains vulnerable to a single bad day on one small planet. Every step toward the stars is a step toward making the human experiment more resilient, more durable, more likely to persist long enough to fulfill whatever potential this improbable, curious species actually has. Stephen Hawking said it plainly in the last years of his life. He believed that humanity must become a multi-planetary species to survive the next century, and a multi-stellar species to survive the next millennium. He wasn't being dramatic, he was doing risk assessment. But there's a dimension of this transformation that goes beyond survival, one that is harder to quantify, but perhaps more important to understand. It's the question of identity. What does it mean to be human when humans exist in multiple star systems? Right now, human identity is layered but ultimately grounded in a shared planet. Whatever our cultural differences, and they are vast, every human being on Earth breathes the same atmosphere, drinks water from the same hydrological cycle, evolved under the same sun, looks up at the same moon. We are at the biological and planetary level, one people of one world. Our diversity is real and profound, but it rests on a foundation of shared origin, shared environment, shared cosmic address. Interstellar expansion breaks that foundation. A colony at Proxima Centauri, after a few generations, would not share our sky. They would look up and see different stars. Their sun, our sun, would be a point of light in their night sky, no more personally significant than any other bright star is to us. Their gravity, if they live on Proxima b, might be subtly different. Their radiation environment, their day-night cycle or lack of one, their ecosystem, if they build one, would be alien to ours in ways that would compound over generations, over centuries. The biological and cultural divergence between Earth humans and Proxima humans could become significant. Over millennia, it could become profound. We might, in a very deep sense, become different kinds of people, adapted, evolved, culturally shaped by different stars, different environments, different histories. Is that loss? Is that gain? Is it both? I think it's both. The loss is real, the loss of the shared ground that makes communication and understanding between humans possible. The gain is also real, the extraordinary diversification of what human life can be, the multiplication of perspectives, the resilience of variety. The same way that biological diversity makes ecosystems robust, civilizational diversity spread across the stars might make the human story more resilient, more creative, more capable of surviving and flourishing across cosmic timescales. There is a concept in philosophy of mind and ethics called the overview effect, named after the psychological transformation reported by astronauts who have seen the Earth from orbit. Edgar Mitchell, who walked on the moon during Apollo 14, described it as a sudden, overwhelming sense of the interconnectedness of everything. A feeling that the boundaries between nations, between peoples, between self and other were arbitrary and fragile in the face of the beauty and fragility of the whole planet seen at once. Many astronauts have described versions of this experience. It's not universal, but it's common enough to have been studied seriously. The cognitive shift that comes from seeing the Earth as a whole, from genuinely understanding in your body, rather than just your mind, that this is all there is right now, it changes people. Often permanently. Now ask yourself, what is the interstellar version of the overview effect? What happens to a human consciousness that has genuinely crossed the gulf between stars, that has lived through years of void, of total separation from everything our species has ever known, and arrived at another sun, looked back and seen our solar system as a faint smudge of light, if visible at all? What perspective does that generate? What sense of the scale and the beauty and the improbability of life does it produce? We don't know. No human has ever experienced it. But the astronauts who went to the moon came back changed, and the moon is 384,000 kilometers away. Proxima Centauri is 40.1 trillion kilometers away. The overview effect of an interstellar journey would be orders of magnitude more profound than anything experienced by any human being in history. It might be, quite literally, the most perspective-altering experience a conscious mind could have, and here is what moves me most about that. Whoever those first interstellar travelers are, whatever they experience, Whatever they see, they will come back, or they will transmit, and they will try to tell us. The way every explorer has always tried to tell the people back home what they found, what it looked like, what it felt like to stand somewhere no one had ever stood. That act of communication, of trying to share the unshared, is one of the most deeply human things there is. But let's be honest about the shadow side of this story, because I think intellectual honesty demands it, and because I believe you come to this channel for truth, not comfort. Human expansion has a complicated history. Every time our species has entered a new territory, encountered a new environment, discovered a new world, it has brought not only curiosity and wonder, but also conflict, exploitation, and destruction. The history of human colonialism is written in blood and cultural erasure across every continent on Earth. The history of our impact on the natural world is written in the extinction ledgers of thousands of species that no longer exist. We have not always been good stewards of the worlds we've entered. If Proxima b or any other planet in that system harbors life, even microbial life, even the simplest biochemistry, what are our obligations? Do we have the right to land on it? To introduce our chemistry, our microbes, our presence into an ecosystem that evolved entirely without us? The question of planetary protection is taken seriously in current space exploration. Marslanders are sterilized to extraordinary standards to avoid contaminating Mars with Earth biology. But an interstellar mission with human colonists would be an incomparably greater contamination risk, and if the life is more complex, if there is something on Proxima b that is not just chemistry but genuine biology, organisms with behavior, with adaptation, with the hallmarks of evolutionary complexity, then the question becomes not just biological but moral, and it's one we don't have a consensus answer to. Different philosophical traditions give very different responses. Some say the universe belongs to whoever can reach it. Others say the discovery of extraterrestrial life would impose the most profound moral obligation in human history, to do nothing that harms it. I don't think there's an easy answer. I think there's an important conversation. And I think the fact that we are now in the era where this conversation has practical implications, where the decisions we make in the next century could determine how we behave when we arrive, means we should be having it loudly, thoughtfully, and urgently. Here is what I believe, and I want to be clear that this is my perspective, not established science. The story of humanity reaching the stars is not primarily a story about technology. Technology is the means. The story is about what kind of species we choose to be. Do we go to the stars as conquerors, carrying all the worst of what we are? Or do we go as explorers in the deepest sense, genuinely open, genuinely humble, genuinely committed to understanding before acting? That choice isn't made on the day we launch. It's made in the thousands of days before that, in how we fund science, in how we treat each other, in whether we develop the wisdom to match our ambition. The stars don't care which version of humanity arrives, but the universe we build in the centuries between now and that arrival will be shaped entirely by which version we become. That's not a scientific prediction, it's a call. And I think it's the most important one embedded in this entire conversation about engines and distances and time. We're going to push to the absolute edge of what physics permits and ask, if we could do anything, if resources and time were no object, how fast could we actually go? The answer is going to surprise you. Let's push to the limit. Everything we've discussed so far has operated within the boundaries of what we could plausibly build in the next century or two. Nuclear propulsion, fusion drives, light sails, generation ships, real concepts, grounded in understood physics, facing engineering challenges that are hard but not forbidden, the kind of technology that requires sustained civilizational commitment, not miraculous discovery. But I want to take you somewhere further now, to the edge of what physics actually permits, to the concepts that sit not in the engineering department, but in the theoretical physics department, ideas that are mathematically coherent, that don't violate any known law of nature, but that require either resources or breakthroughs so vast that they belong more to the deep future than to any roadmap we could write today. Because here's the thing about understanding the absolute limits of what's possible. It changes how you think about the journey between here and there. When you know the ceiling, you understand the full height of the room you're standing in. And in this room, the room of interstellar propulsion physics, the ceiling is breathtaking. Let's start with antimatter. Because of all the exotic propulsion concepts seriously discussed in peer-reviewed physics literature, antimatter drives are the closest to being physically straightforward. In the sense that antimatter genuinely exists, we know how it behaves, and we understand exactly why it's so extraordinary as a fuel source. Antimatter is the mirror of ordinary matter. Every particle has an antimatter counterpart. The electron has the positron, the proton has the antiproton, identical in mass but opposite in charge and certain quantum properties. When matter and antimatter meet, they don't just react chemically, they annihilate each other completely, converting 100% of their combined mass directly into energy. Every last gram, every last atom, the implications of that are staggering. Einstein's equation, E equals mc squared, tells us that the energy contained in mass is equal to that mass multiplied by the speed of light squared. The speed of light is approximately 300 million meters per second. Squaring that number produces an almost incomprehensible energy density. 1 gram of matter, fully annihilated with 1 gram of antimatter, releases the energy equivalent of roughly 21 kilotons of TNT, comparable to the bomb that destroyed Hiroshima, not from a kilogram, from a gram, 2 grams total. A rocket fueled by matter-antimatter annihilation would have a specific impulse, a measure of fuel efficiency, orders of magnitude beyond any other propulsion system ever seriously considered. Theoretical analyses suggest that an antimatter drive could propel a spacecraft to somewhere between 40 and 80% the speed of light, depending on the design and the fraction of annihilation energy successfully converted to thrust. At 50% the speed of light, a journey to Proxima Centauri would take about 8.5 years as measured from Earth. For the crew, thanks to time dilation at that speed, the experience time would be closer to 7.5 years. A single human career, the kind of time frame that doesn't require generation ships or radical life extension or suspended animation, a mission you could volunteer for at 30 and complete before you turn 40. So why aren't we building antimatter drives? 2 reasons, and both of them are genuinely formidable. The first is production. Antimatter doesn't exist in stable quantities in nature, at least not in our observable universe, which is itself one of the deepest mysteries in modern physics. We know the Big Bang should have produced equal amounts of matter and antimatter. We know that when they meet, they annihilate. We know our universe is made almost entirely of matter. Where did all the antimatter go? That question, the matter-antimatter asymmetry problem, is one of the great unsolved problems in particle physics. What this means practically is that every antiproton, every positron we want to use as fuel has to be manufactured, created in particle accelerators by smashing high-energy promes together and capturing the resulting antiparticles before they annihilate with surrounding matter. This process is extraordinarily inefficient. CERN, the European Organization for Nuclear Research in Geneva, home of the Large Hadron Collider, produces antiprotons regularly. In a full year of operation, CERN produces roughly 15 nanograms of antihydrogen, 15 billionths of a gram. A mission to Proxima Centauri using an antimatter drive would require something on the order of tens of grams to hundreds of kilograms of antimatter, depending on the ship's mass and design. At CERN's current production rates, manufacturing enough antimatter for an interstellar mission would take longer than the age of the universe. To make antimatter propulsion viable, we would need to improve antimatter production efficiency by many orders of magnitude, likely requiring dedicated space-based production facilities powered by enormous solar arrays, capturing every antiparticle with near-perfect efficiency and storing it in magnetic confinement systems that don't yet exist at the required scale. The physics of how to do this isn't forbidden. The engineering gap is simply enormous. The second problem is storage. Antimatter cannot touch any ordinary matter container. The instant it does, annihilation occurs. Storing it requires magnetic or electric fields that keep it levitated and isolated. Current magnetic confinement systems can hold small quantities for limited periods. A spacecraft carrying kilograms of antimatter on a decades-long journey would need confinement systems of extraordinary reliability. Failing once, even briefly, would be catastrophic in the most literal sense. These are not insurmountable problems. They are engineering problems, even if they are engineering problems at a scale we can barely currently imagine. The physics is not in the way. Human ingenuity and time and resources are what stand between us and antimatter propulsion. Now let's go further. Past antimatter, past fusion, past everything with a clear engineering pathway, and into territory that theoretical physicists discuss with a mixture of rigor and wonder. The Alcubierre drive. In 1994, Mexican theoretical physicist Miguel Alcubierre published a paper in the journal Classical and Quantum Gravity that caused a quiet sensation in the physics community. Working entirely within the framework of Einstein's general theory of relativity, not violating it, but exploiting its deepest implications, Alcubierre described a theoretical mechanism by which a spacecraft could travel between 2 points faster than the speed of light, without the occupants of the spacecraft ever locally exceeding light speed. The concept works, in simplified terms, like this. General relativity tells us that spacetime itself can be curved, stretched, and compressed by mass and energy. This isn't speculation, it's one of the most precisely tested theories in science. GPS satellites require corrections for space-time curvature to function accurately. The detection of gravitational waves by LIGO in 2015 directly confirmed that space-time can ripple and propagate. Alcubierre's insight was to ask, what if you could engineer a bubble of space-time around a spacecraft that contracts the space in front of it and expands the space behind it? The spacecraft inside the bubble wouldn't be moving through space in the conventional sense. It would be sitting still in its local environment, perfectly comfortable, experiencing no acceleration. But the bubble of space-time it sits in would be moving, and there is no known speed limit on how fast space-time itself can move. In principle, an Alcubierre drive could deliver a spacecraft across 4.24 light-years in days, in hours, in whatever time the designer specifies, limited not by the speed of light, but by the energy available to manipulate spacetime. Let me be precise about the current scientific status of this idea, because I believe you deserve precision. The Alcubierre metric is mathematically valid. It is a legitimate solution to Einstein's field equations. It does not contain any internal contradiction that physics has identified. In that sense, it is not dismissed as science fiction by serious physicists. It is discussed, analyzed, and debated in the peer-reviewed literature. However, the challenges are profound. The energy required to create an Alcubierre bubble in the original 1994 formulation was calculated to be on the order of the total mass energy of Jupiter, converted entirely to exotic negative energy, not positive energy, exotic negative energy, a form of energy density that is theoretically permitted by quantum field theory in very small quantities. The Casimir effect produces measurable negative energy density between closely spaced metal plates, but has never been produced or observed at macroscopic scales. Subsequent refinements to the concept have reduced the theoretical energy requirements significantly. Harold White at NASA's Johnson Space Center published work in 2012 suggesting that modifications to the bubble's geometry could reduce the energy requirement by many orders of magnitude. His group conducted laboratory experiments attempting to detect tiny distortions in spacetime. The results were inconclusive but not null. More recent theoretical work has raised additional challenges, including arguments that an Alcubierre bubble might be inherently unstable, that causality violations could make it physically unrealizable, and that the exotic matter required might not exist in the forms needed. The scientific community has not reached consensus. The drive remains theoretically interesting and practically far beyond anything we know how to build, but it is not ruled out. And in physics, not ruled out is a place where extraordinary things sometimes eventually happen. There is another concept worth knowing, one that sits between the near-term plausibility of light sails and the far-future speculation of warp drives. It's called the laser highway, or sometimes the beamed energy infrastructure concept. The core idea is this: instead of a spacecraft carrying its own propulsion energy, which is the fundamental problem of every rocket design, the reason spacecraft are mostly fueled by mass, what if the energy source stays at home and the spacecraft is pushed remotely? We've already discussed the basic version of this with breakthrough Starshot, a ground-based laser array pushing a light sail nanocraft. But the laser highway concept scales this up and extends it. Imagine a network of laser arrays distributed throughout the solar system, at Earth, at Mars, at stations in the asteroid belt, perhaps eventually in the outer solar system, each one capable of focusing an enormous beam of energy on a passing spacecraft and contributing to its acceleration. As the spacecraft moves outward, each station in the network takes its turn contributing thrust. The spacecraft accelerates continuously, handed off from one station to the next like a relay race across the solar system, before achieving a final velocity that no onboard propulsion system could match. Then, at the destination end, a similar network, if one has been established by earlier missions, could provide deceleration. This concept elegantly solves one of the hardest problems in interstellar mission design, the deceleration problem. Accelerating a light sail to 20%, the speed of light using a laser array, is challenging but theoretically manageable. Stopping it at the other end, without a laser array there to push back against, that's where the physics becomes genuinely brutal. A spacecraft arriving at Proxima Centauri at 20% the speed of light and unable to decelerate would fly through the system in a matter of hours, far too fast to conduct any meaningful science or enter orbit. The laser highway concept, with relay infrastructure at both ends, addresses that. It also points towards something larger, the idea that interstellar travel might not be a single heroic mission, but an infrastructure project. Something built incrementally, expanded over centuries, eventually becoming as routine as the shipping lanes that now connect Earth's ports. Now I want to bring this section home with something that I think reframes the entire conversation about propulsion limits. Every concept we've discussed, nuclear pulse, fusion drives, antimatter engines, light sails, Alcubierre drives, laser highways, has one thing in common: they were conceived by human minds, working with the physics we currently understand. Within the time frame of the last century, we have been doing modern physics for about 100 years. The universe has been doing physics for 13.8 billion years. We are, in terms of our understanding of nature, extraordinarily young. The history of science is a continuous record of discoveries that overturned what everyone thought were fundamental limits. The sound barrier, thought unbreakable, was crossed in 1947. Heavier-than-air flight, declared impossible by serious scientists, happened in 1903. The manipulation of individual atoms, science fiction, until the 1980s is now routine nanotechnology. There is no reason, none, to believe that the physics we understand today is the complete physics of the universe. General relativity and quantum mechanics, the two great pillars of modern physics, are mutually incompatible at their foundations. We know they are both incomplete. A theory of quantum gravity, one of the holy grails of theoretical physics, would fundamentally reshape our understanding of space, time, energy, and matter. What that theory might permit, what technologies it might enable, we cannot know. Because we don't have it yet, the history of science suggests we should be humble about declaring limits. Every generation has drawn lines around the possible. Every generation has been surprised. The fastest we could ever go. We genuinely don't know. We know the limits of our current physics. We do not know the limits of physics itself. And that, in a universe this large, this old, this generous with its wonders, is one of the most exciting sentences in the human language. Science doesn't happen in a vacuum. I know that sounds ironic, given that we've spent this entire video talking about the vacuum of space. But what I mean is this: behind every equation, every mission concept, every breakthrough in our understanding of how to reach another star, there is a human being, someone who woke up one morning, or stayed up until 3 in the morning, consumed by a question that most people around them didn't take seriously. Someone who chose the long road, the underfunded road, the road that promised no guarantee of recognition in their own lifetime. The story of interstellar science is not just a story of physics and engineering. It is a story of stubbornness, of passion sustained across decades, of people who looked at an impossible problem and decided quietly and firmly that it was worth their one life. I want to introduce you to some of them, not as names in a textbook, as people. Let's start with a man most people outside the aerospace world have never heard of, and that is a genuine injustice. Konstantin Tsiolkovsky was born in 1857 in a small village in rural Russia. He was largely self-educated. A childhood illness had left him nearly deaf, isolating him from formal schooling and, in a way, from the noise of conventional thinking. He became a mathematics teacher in a provincial town called Kaluga, living modestly, spending his evenings working through the mathematics of rocket propulsion in a tiny study that was barely more than a closet. In 1898, 5 years before the Wright brothers flew at Kitty Hawk, Tsiolkovsky derived the rocket equation, the fundamental mathematical relationship that governs all rocket propulsion, the equation that relates a rocket's change in velocity to the exhaust velocity of its propellant and the ratio of its initial to final mass. This equation, still called the Tsiolkovsky rocket equation today, is the bedrock of all spaceflight. Every mission that has ever left Earth, from Sputnik to the Apollo program to the James Webb Space Telescope, was designed with this equation at its foundation. Tsiolkovsky didn't stop there. He wrote extensively about liquid-fueled rockets, multi-stage rockets, space stations, airlocks, closed-loop life support systems, and the colonization of the solar system. In 1903, the same year the Wright brothers made their first powered flight, he published a paper titled The Exploration of Cosmic Space by Means of Reaction Devices. It described, with mathematical rigor, the principles of liquid-fueled rocketry decades before the technology existed to test them. He was not taken seriously in his lifetime. He lived in poverty, working in a provincial backwater, publishing in obscure journals that few people read. He died in 1935, having seen the very early stages of rocketry begin to validate his work, but never seeing a rocket actually reach space. His most important contributions were recognized fully only after his death, when the Soviet space program, and through competing ambition, the American one, built the technology he had mathematically described. He is buried in Kaluga. A statue stands outside the local history museum, and every time a rocket lifts off anywhere in the world, the mathematics in its flight computer traces back to a deaf schoolteacher in rural Russia who spent his evenings dreaming about the stars. Hermann Oberth was born in 1894 in Transylvania, in what is now Romania. As a child, he read Jules Verne's From the Earth to the Moon and was electrified by it, not as fantasy, but as a challenge. He decided, at the age of 11, that he would spend his life figuring out how to actually do it. He did exactly that. Decades before space travel was taken seriously by governments or militaries, Oberth was working through the mathematics of multistage rockets, orbital mechanics, and space telescopes. In 1923, he self-published a book called The Rocket into Planetary Space, after his doctoral dissertation on rocketry was rejected by the University of Heidelberg as being too speculative. The book became enormously influential in European rocketry circles, inspiring a generation of young engineers and scientists, including a teenager named Wernher von Braun. Von Braun, of course, went on to lead the development of the V-2 ballistic missile for Nazi Germany during World War II, a deeply morally compromised chapter, before being brought to the United States under Operation Paperclip, where he became the chief architect of the Saturn V rocket that carried Apollo astronauts to the moon. The ethical complexity of that story is real and unresolved, but the technical lineage is undeniable, from Verne to Oberth to von Braun to the moon, a chain of inspired and inspiring and sometimes troubling human beings, each passing the torch to the next. Oberth lived to 94, long enough to witness the moon landing he had dreamed about as a child. He reportedly watched the Apollo 11 launch in person as a guest of NASA. The child who read Jules Verne in Transylvania lived to see human beings walk on another world. Robert Goddard is the third of the founding trinity of rocketry, and perhaps the most poignant figure in this story. Goddard was American, born in 1882 in Worcester, Massachusetts. Like Tsiolkovsky and Oberth, he arrived at rocketry through pure intellectual passion, spending years working through the mathematics and then, crucially, building and testing actual hardware. On March 16, 1926, in a snow-covered field in Auburn, Massachusetts, Goddard launched the world's first liquid-fueled rocket. It reached an altitude of about 12.5 meters and flew for 2.5 seconds. It sounds modest. It was historic. It was the first time a rocket powered by liquid fuel had flown under its own power. Every liquid-fueled rocket in the world today is the technological descendant of that sputtering 12-meter hop in a New England field. But Goddard was mocked, publicly and cruelly. A 1920 editorial in the New York Times ridiculed his idea that rockets could function in space, incorrectly claiming that without air to push against, a rocket couldn't generate thrust. The editorial was wrong. It reflected a fundamental misunderstanding of Newton's third law, but it was published in the most prominent newspaper in America, and it damaged Goddard's reputation and made him deeply reluctant to publish his work openly for the rest of his life. He worked largely in secret in the desert of New Mexico, funded modestly by the Guggenheim family, watched warily by the American military who weren't sure what to make of him. He died in 1945, before the space age he had done so much to make possible. The New York Times published a correction to its 1920 editorial in July of 1969, the day after Apollo 11 launched toward the moon. 49 years late, Goddard never received the recognition he deserved while he lived. Today, NASA's Goddard Space Flight Center in Maryland, one of the most important research institutions in the history of spaceflight, bears his name. A small correction, better than nothing. When we move from the founders of rocketry to the pioneers of specifically interstellar thinking, one name stands above the others in terms of sheer creative breadth: Freeman Dyson. Dyson was born in England in 1923 and spent most of his career at the Institute for Advanced Study in Princeton, the same institution where Einstein spent his final decades. He was one of those rare minds who combined extraordinary mathematical ability with an almost childlike willingness to ask questions that more cautious scientists considered embarrassing. We've already mentioned his work on Project Orion, the nuclear pulse propulsion concept. But Dyson's contributions to interstellar thinking go far beyond that. He proposed the Dyson sphere, a theoretical megastructure that a sufficiently advanced civilization might build around its star to capture all of its energy output. He wrote seriously about the possibility of life in interstellar space, in comets, in the far future of a cooling universe. He thought about the long-term future of intelligence in the cosmos, with a rigor and an openness that few scientists have matched. What distinguished Dyson was his refusal to be limited by what was currently fashionable in physics. He once wrote that science is not just a collection of facts, but a way of asking questions that haven't been asked yet. He spent his career modeling that principle. He died in February of 2019 at the age of 95, still intellectually active, still publishing, still asking the big questions. His legacy is not a single discovery but an entire style of thinking, expansive, unafraid, grounded in mathematics but not imprisoned by convention. The kind of thinking that interstellar science desperately needs and too rarely gets. Carl Sagan occupies a different category from the engineers and theorists we've been discussing. He was an astrophysicist and planetary scientist of genuine distinction. His work on the greenhouse effect of Venus's atmosphere, on the seasonal changes on Mars, on the potential habitability of Titan were serious scientific contributions. But his most enduring legacy was something harder to quantify. He was the person who made the cosmos feel personal. Sagan understood, more deeply than almost anyone of his generation, that the emotional and psychological dimensions of space exploration were as important as the technical ones, that humans would not commit civilizational resources to the stars purely on the basis of equations, that they needed to feel it, to feel the wonder, the smallness, the connection, the urgency of looking up and asking what's out there. His television series, Cosmos, which first aired in 1980, was watched by more than 500 million people in 60 countries. It remains one of the most watched documentary series in the history of television. It did not dumb down science. It elevated its audience, trusted their intelligence, and treated them as fellow travelers in the human adventure of understanding. Sagan also co-founded the SETI Institute, the search for extraterrestrial intelligence, and was a passionate advocate for the scientific legitimacy of asking whether we are alone in the universe. At a time when that question was considered fringe by mainstream academia, Sagan argued forcefully that it was among the most scientifically and philosophically important questions a civilization could ask. History has vindicated him. The search for biosignatures on exoplanets is now one of the most active and well-funded areas of astronomy. He died in December of 1996 at 62 of pneumonia following complications from myelodysplasia, far too soon. The field of science communication, of public engagement with astronomy and astrophysics, lost its greatest practitioner. But the seeds he planted, in millions of children who watched Cosmos and decided to become scientists, in the institutional legitimacy he gave to SETI, in the cultural framework he built for thinking about our place in the cosmos, those seeds are still growing. Every video like this one, every person who makes science feel like the human adventure it is working in the tradition Carl Sagan created. More recently, a new generation of interstellar advocates has emerged, people working not just in theory but in active program development. Philip Lubin at the University of California, Santa Barbara has been one of the driving scientific forces behind the photonic propulsion concept, the physics that underlies breakthrough Starshot. His work on directed energy propulsion, much of it funded by NASA's innovative Advanced Concepts program, has moved laser-driven light sails from a science fiction staple to an engineered concept with a concrete development roadmap. Lubin is one of those scientists who combines deep theoretical understanding with a genuine hunger to see things actually built, a rarer combination than it sounds. Avi Loeb at Harvard has become perhaps the most publicly prominent advocate for ambitious interstellar science in recent years, and one of its most controversial figures. His scientific contributions to the theory of the early universe, to the first stars and black holes, are well regarded, but it is his willingness to entertain radical hypotheses, including the possibility that the interstellar object Oumuamua, which passed through our solar system in 2017, might have been an artifact of an extraterrestrial civilization, that has made him both celebrated and criticized. Whatever one thinks of Loeb's specific hypotheses, his broader argument is important, that the search for extraterrestrial intelligence and the development of interstellar capability deserve the same rigorous, well-funded scientific attention as any other frontier in astrophysics. That stigma around these questions is not scientific. That dismissing ideas without examination is as bad as accepting them without evidence. He is also the founding director of the Galileo Project, a systematic scientific search for evidence of extraterrestrial technological artifacts using arrays of wide-field telescopes and sophisticated data analysis. Controversial, yes, but being done with genuine scientific rigor, the kind of open-minded, evidence-based inquiry that Sagan would have recognized and, I think, applauded. And then there are the thousands of people whose names you will never know. The graduate students who spent 5 years on a thesis about electromagnetic sail deployment mechanisms, the engineers who ran thermal models on hypothetical fusion reactor designs, the astrobiologists who catalogued the survival limits of extremophiles in hopes of understanding what life might look like on a tidally locked world, the mission planners who mapped out communication protocols for probes that won't be launched for a century. These people are doing the work that makes the dream possible. They are not heroes in the public sense. They are not household names. They go to work every day in universities and research centers, sustained mostly by curiosity and the belief that their contribution, however small, is part of something that will one day matter enormously. The stars will be reached, if they are reached, because of them, because of the invisible labor of people who cared enough to spend their best years on a problem that no one expected them to solve in their lifetime. That's one of the most profoundly human things I can think of, to do important work for the benefit of people you will never meet in a future you will never see, to be one link in a chain that stretches from a deaf mathematics teacher in rural Russia all the way to the first light of Proxima Centauri seen from a human eye. There is one more figure I want to mention before we close this part. Not a scientist, not an engineer, a writer. Olaf Stapledon was a British philosopher and author who in 1930 published a novel called Last and First Men. It told the history of humanity across 2 billion years, across 18 distinct human species, migrations to other planets, extinctions and rebirths, the slow spread of mind through the solar system. In 1937, he published Star Maker, a visitation of the entire history of intelligence in the cosmos, from its earliest stirrings to its ultimate fate. These books were not popular fiction. They were difficult, philosophical, dense, but they were read by the people who mattered most. Arthur C. Clark called Stapledon one of the greatest influences on his work. C.S. Lewis, Bertrand Russell, Freeman Dyson, they all read him. They were all shaped by the scope and seriousness of his imagination. What Stapledon gave the interstellar community was not equations or engineering. He gave it a canvas large enough to paint the actual scale of the problem, a felt sense of what it would mean to be a civilization that truly took the long view, that thought in billions of years rather than budget cycles. He gave ambition a place to live. Science needs its poets as much as it needs its mathematicians. The people who can hold the full enormity of the question and not flinch from it, who can communicate that enormity to others and make them feel it rather than just understand it, are as essential to the interstellar project as any propulsion engineer. You are here watching this video because somewhere in your life, a book or a film or a documentary or a clear night sky made you feel the scale of the universe and left you permanently changed by it. Someone gave you that. Someone worked to make that possible. That gift passes forward. Always, if you are still watching, please subscribe to this channel and give a like. You will join a community that explores the cosmos together. Now we're going to stand at the summit of everything we've climbed through and look in both directions, back at where we started and forward at where this all leads. We're going to ask the final question, the one underneath all the others, the one that this entire video has really been building toward. Not just how long would it take us to reach Proxima Centauri, but why does it matter that we try? The answer is going to be worth the wait. We started this video with a number, 4.24 light years, 40.1 trillion kilometers, the distance between our sun and the closest star that isn't it. A number so large that every unit of measurement we use in daily life collapses into meaninglessness trying to contain it. A number that, when you first encounter it, feels less like a distance and more like a wall. And then we spent this entire video dismantling that wall, piece by piece, concept by concept. We looked at what our fastest current spacecraft would take, tens of thousands of years, and we looked at what nuclear propulsion might achieve, centuries. We looked at fusion drives and their decades. We looked at light sails and their 20-odd years. We looked at antimatter and its single human lifetime. We looked at concepts so advanced they belong to a physics we haven't fully written yet. We traveled through time dilation and discovered that the universe has a strange mercy built into its speed limit, that the faster you go, the shorter the journey feels from the inside. We sailed through the sociology of generation ships and felt the weight of what it means to be born in transit, to inherit a mission you didn't choose, to live and die on the way to somewhere you'll never see. We orbited Proxima b and stared at its data, rocky, potentially watered, radiation-battered, stubbornly ambiguous, and felt the particular ache of a question that science is close to answering but hasn't answered yet. We met the people who gave their lives to this problem. The deaf schoolteacher with his rocket equations, the mocked American inventor in a New Mexico desert, the physicist who refused to stop asking embarrassing questions, the man who made 500 million people feel the cosmos personally, the graduate students and mission planners and astrobiologists whose names will never trend but whose work is the real foundation of everything. And now we're here, at the end, at the question that was always underneath all the other questions, not how long would it take, why does it matter that we try? I want to answer that question honestly, not with the easy answers, not because it's in our nature to explore, or because the universe is calling, though both of those things are true and worth saying. I want to answer it in a way that I hope lands differently, more personally, more urgently. Here is the first reason. We are, as far as we currently know, the only part of the universe that knows the universe exists. Think about that for a moment. Really let it settle. The cosmos is 13.8 billion years old. It contains somewhere between 100 billion and 2 trillion galaxies, each containing hundreds of billions of stars, many of those stars hosting planets, many of those planets sitting in the temperature range where chemistry becomes interesting. It has been doing this, expanding, evolving, complexifying, for longer than the human mind can genuinely hold. And yet, as far as our best science can currently tell us, it has only ever produced one confirmed example of a mind that can look back at it, one planet around one star in one unremarkable corner of one galaxy, where matter organized itself into creatures capable of curiosity, creatures who built telescopes and equations and spacecraft, creatures who looked up at the dark and asked, "What is that? And can we reach it?" That is extraordinary, possibly unique, certainly precious. If we are alone, if this is the only place in the universe where the cosmos has achieved self-awareness, then every human mind is an irreplaceable instrument of cosmic self-knowledge. Every scientist, every artist, every child who ever looked up at a night sky and felt the pull of those points of light is the universe knowing itself. And the extinction of that awareness would be the universe going blind. If we are not alone, if there is life at Proxima b, if there are minds somewhere among those 2 trillion galaxies that have also looked up and wondered, then the question of whether we reach out, whether we make contact, whether we become the kind of civilization that does not stay home and wait, becomes even more urgent. Because then the universe is full of minds that have never met, and the conversation that could happen between them across the light years is something the universe has never experienced before. Either way, it matters. Either way, the answer to why reach for the stars is the same, because consciousness in a cosmos of that scale is too rare, too precious, too extraordinary to remain confined to one pale blue dot around one ordinary star. Here is the second reason, and this one is closer to home, the act of reaching toward Proxima Centauri, the sustained, multi-generational, civilizational commitment to a goal that will not be achieved in any individual lifetime, is itself transformative. Not because of what we find when we get there, but because of what the reaching makes us. Consider what building toward interstellar travel requires. It requires that we solve fusion energy, which would give us effectively unlimited clean power on Earth, ending energy poverty and dramatically reducing the carbon cost of human civilization. It requires advances in closed-loop life support, the ability to sustain human life in complete ecological isolation, which has direct applications to making human civilization more resilient on Earth itself. It requires genetic science capable of maintaining diversity across generations in isolated populations, knowledge that could transform medicine. It requires artificial intelligence sophisticated enough to conduct autonomous scientific exploration, technology that will reshape every aspect of human life long before any probe reaches another star. The technologies we develop on the path to the stars will not stay on the path to the stars. They never have. Teflon, memory foam, water filtration systems, scratch-resistant lenses, the digital camera sensor. These are all technologies developed for space exploration that found their way into everyday human life. The spin-offs from a serious, sustained interstellar program would be incomparably greater. The path to another star is paved with solutions to problems we haven't solved on Earth yet. This is not a secondary benefit. It is an argument. The investment in reaching the stars is an investment in the quality of human life right here, on this planet right now. Here is the third reason, the most personal one. We are made of stars, not metaphorically, not poetically, though it is both of those things. Literally, chemically, physically, the carbon in your body was forged in the nuclear furnace of a star that lived and died billions of years before our sun was born. The oxygen in your lungs, the iron in your blood, the calcium in your bones, all of it was synthesized in stellar interiors and scattered into the cosmos by supernova explosions drifting through space for billions of years before gravity gathered it into the cloud that eventually became our solar system, our planet, and ultimately, you are recycled starlight. You are the universe organized into a form that can wonder about the universe. When we reach for the stars, we are not leaving home. We are returning to it. We are closing a loop that began 13.8 billion years ago, when the first atoms of hydrogen collapsed under gravity into the first stars, and those stars burned and died and scattered the seeds of everything that would eventually think and feel and love and ask questions. The interstellar journey is not humanity's departure from nature. It is humanity's fullest expression of it. We are what the cosmos made, and the cosmos through us is reaching back toward itself. That is not mysticism. That is nuclear astrophysics and evolutionary biology and cognitive neuroscience, assembled into a sentence that happens to also be true. Now I want to address something directly, because I think it needs to be said. There are people, thoughtful, serious people, who look at the interstellar project and feel a kind of moral discomfort, who ask, why are we spending energy dreaming about stars 4 light-years away when there are people suffering on the planet we already have? When there is climate change to address, poverty to eliminate, diseases to cure, injustices to correct? It's a fair question. It deserves a real answer, not a dismissal. Here is mine. The premise of that question, that we must choose between caring about Earth and reaching for the stars, is false. It is a false binary that has been used throughout history to argue against every ambitious scientific program, every long-horizoned investment in human knowledge. It was used to argue against the Apollo program, against the development of the Internet, against the Human Genome Project. In every case, history showed that the ambitious program did not steal resources from solving immediate human problems. It generated new resources, new capabilities, new solutions that no one had anticipated. The technologies, the trained minds, the institutional knowledge, the cultural inspiration, all of it fed back into the broader project of human flourishing. More fundamentally, a civilization that loses the capacity to dream about the long future is a civilization in danger of losing the will to invest in it. The ability to look beyond the immediate crisis, to ask where we want to be in 1,000 years, in 10,000, is not a distraction from solving today's problems. It is the source of the meaning that makes solving them feel worthwhile. We do not have to choose between feeding the hungry and reaching the stars. We have to become the kind of civilization that is capable of both. And the aspiration to reach the stars is part of what builds that civilization. So, how long would it really take us to reach Proxima Centauri? With our fastest current spacecraft, roughly 75,000 years. With near-future nuclear propulsion, it would take centuries. With mature fusion drives or advanced light sail technology, decades. With antimatter propulsion, if we develop it, a single human lifetime. With technologies we don't yet know how to build, exploiting physics we don't yet fully understand, potentially far less. And with robotic probes, small, fast, autonomous, intelligent, potentially within the lifetimes of children alive today. Within the next 50 to 100 years, if the will and the funding align, there is no single answer. There is a spectrum. And where we land on that spectrum depends entirely on choices we make right now. How much we invest in fundamental science, how seriously we take the long view, how willing we are to begin journeys we know we won't finish personally, trusting that the generations after us will carry the work forward. Every civilization that has ever achieved something lasting made bets on a future they would never see. The people who planted the forests, that built the ships, that carried the explorers, who mapped the continents, had no idea what their forests would eventually make possible. They planted anyway. We are at the planting stage of interstellar civilization. The trees are small, the forest is barely visible, but it is alive, and the people tending it, in university labs and space agency research centers and backyard telescopes and curious minds all over this planet, are doing something that will matter for as long as there are minds to remember it. If this video has done what I hoped it would, you're not ending it with a cleaner, simpler answer than you arrived with. You're ending it with a better question. Not just how long would it take, but what are we willing to do to make it possible? Not just can we go, but who do we want to be when we get there? Not just how far is it, but what does the reaching say about us? The distance to Proxima Centauri is 4.24 light-years. The distance between who we are and who we'd need to become to cross it is harder to measure, but it is, I believe, a distance we are capable of traveling. We have been traveling it slowly for the entire history of our species. Every question asked, every boundary pushed, every mind opened to the scale of what the universe actually is. You are part of that travel, right now, simply by caring enough to watch a video like this, to sit with these ideas, to let them work on you. Curiosity is not passive, it is the first engine, the one that makes all the others possible. The stars are out there. They have been there for billions of years, long before anything on Earth existed to look up at them. They will be there long after our sun expands and swallows this pale blue dot, and the last photon from Earth's final sunset disperses into the cosmic dark. But right now, in this tiny, improbable, beautiful window of time, there are minds here that can see them, that can measure them, that can dream about reaching them. That is the most extraordinary fact in the universe. And if your mind is still racing after all of that, then click the video on the screen, because the next logical question is the one most people are afraid to ask seriously. What would it actually take to travel faster than light? Not science fiction, not hand-waving, the real physics, the real proposals, and just how close we actually are. That video is on your screen right now.